So yesterday, my video, I stopped at the formula on resistors, the power rating. Now I'm just going through it, briefly. I'm not going too much into detail with it until I look at a schematic and then we can do the math and all that. There's still quite a bit to go through. So that's the power formula. Power is usually calculated by multiplying the voltage and current. I know I stands for current, V is for voltage, and P is obviously power. By applying Ohm's law, we can use the resistance value in calculating power. So if we know the current running through a resistor, we can calculate the power as power equals current to the power of 2 times the resistance. But if you know the voltage across a resistor, the power can be calculated as P equals V to the power 2 divided by the resistance. You have series and parallel resistors, and then you have this thing called capacitance, which there's math for that too. Resistors are paired together all the time in electronics, usually in a series or parallel circuit. When resistors are combined in series or parallel, they create a total resistance, which can be calculated using one or two equations. Knowing how resistor values combine comes in handy if you need to create a specific resistor value. So a series resistors is when connected in series, they simply add up. So, oops, I didn't mean to click that thing. Well, that's what it looks like. Let me click back. I didn't mean to click it. And is my thing, okay, it's not muted. So when I'm playing like Worms Armageddon and stuff, it's muted. But anyways, so you have a resistor right here, another one, I don't know what that is. And then you have this resistor and that. So I don't know what the TOT stands for. Equals resistor 1 plus resistor 2 plus Rn minus 1 plus Rn. So in resistors in series, the total resistance is the sum of all series resistors. For example, if you have two, you have to have a 12.33k resistor. And I'll go over the 33k and the M and all that. What does that, mean? To seek out some more common resistor values, 12k, 330 ohms, and butt them up together in series. And then you have parallel. So it's just 1 over whatever that TOT means equals. This one's R. TOT equals. It says the inverse of resistance is actually called conductance. So to put it more, I can't say that succinctly, the conductance of parallel resistors is the sum of each of their conductances. As a special case of this equation, if you have just two resistors in parallel, their total resistance can be calculated with the slightly less inverted equation. So you multiply the top and then you add the bottom and then you divide the two. As even more special case of that equation, if you have two parallel resistors of equal value, the total resistance is half of that value. So if you have two 10k resistors that are in parallel, their total resistance is 5k. A shorthand way of saying two resistors are in parallel is by using the parallel operator, that symbol. So if R1 is in parallel with R2, right, the conceptual equation would be written as R1 parallel to R2. Much cleaner and hides all those nasty fractions. Resistor networks. So as a special introduction to calculating total resistance, electronics teachers just love to subject their students to finding that crazy convoluted resistor networks. A tame resistor network question might be something like, what's the resistance from terminals A to B? To solve such a problem, start at the back end of the circuit and simply simplify towards the two terminals, in that case R7, R8, and R9. Where's that at? Okay. R7, R8, and R9 are all series and can be added together. Those three resistors are in parallel with R6. Parallel, 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 right? Which one was it? 7, 8, 9. And so you add them all up because they're parallel to R6. So those four resistors could be turned into just one with the resistance of R6 parallel to R7, R8, R9. Since all three of these are parallel to R resistor 6, making our circuit look like that instead of this. So technically you just, looks like you kept R1, R2, R3, R4, R5, but it turns R6 to R7, R8, R9. So you just got rid of that, all that crap. So now the four rightmost resistors can be simplified even further, right? R4, R5, and R6. R4, R5, and our conglomeration of R6 minus R9. Minus through R9 are all series that can be added. The no series of resistors are all in parallel with R3. So it just kind of repeats. R7, R8, R9 is parallel to R6, so you combine the three. And then you could say that R5, R4, R5, and R6 are all parallel to resistor 3. So now you have R3 parallel, R4, R5, R6 parallel, R7, R8, R9, right? And that's just three series resistors between A, B terminals. Add them up, so the total resistance of a circle is R1 plus R2 plus R3 parallel, which 3 is in parallel of R4, R5, and R6 in parentheses. Then R6 is in parallel with R7, R8, and R9. Example applications, resistors exist in just about every electronic circuit ever. LED current limiting. They're key in making sure LEDs don't blow up when power is applied. When connecting a resistor in series with an LED, current flowing through the two components can be limited to a safe value. So that's a resistor. I don't know what that is. That might be the power. Don't know what that is, and that's the LED. When sizing out a current limiting resistor, look for two characteristic values of the LED. The typical forward voltage, I guess that's what that means, and the maximum forward current. So F stands for, I guess, forward, right? But what is... I'm just gonna not pretend I know what that means. I really don't. But anyways, the typical forward voltage is the voltage which is required to make an LED light up. It varies, usually between 1.7 volts and 3.4 volts, depending on upon the color of the LED. The maximum forward current is usually around 20 milliamps. For basic LEDs, continuous current through the LED should always be equal to or less than the current rating. So yeah, I'm gonna say sometimes. So when I see products that say 1.7 volts, 3 volts, 20 watts, 30 watts, 15 watts. Now when you vape, you probably have a vape in your home. Everyone's probably had a vape or tried a vape in their lifetime. And they say that vape, it produces, 15 to 30 wattage. And somewhere between 1 to 1.5 to something voltage or something, right? We'll talk about that too. So once you've gotten a hold of those two values, you can size up a current limiting resistor with this equation. Resistor, so Vs is the source voltage. Okay, so S is for source and F stands for forward. So it's usually a battery or power supply, which I was right. Okay, so I guess if you're using 9-volt battery, VF and IF are the LED's forward voltage and the desired current that runs through it. So F stands for forward. This is the source, which is the battery. Give me a second. And for example, assume you have a 9-volt battery to power an LED. If your LED is red, it might have a forward voltage of about, which is FV, forward voltage of around 1.8 volts. If you want to limit the current to 10 milliamps, use a series resistor of about 720 ohms. So this is some good stuff. This is very basic, and then you use this, what you call it, you use this to, do your math and stuff. I feel like this is important. You can't just be sticking stuff on your breadboard and hoping it turns on. You might hurt yourself. It may explode in your face. Something could happen. I don't know. Unless you have a robot, to do it for you. But I mean, I wouldn't really, mess around, especially if you got a battery connected to it and you're just adding a bunch of stuff just to see. There's no fun in that if you're just doing stuff randomly. But anyways, so that is that. Okay, so VS, that's source voltage. I rather say it says voltage source voltage, and this is the voltage forward. So this would be the battery. Like, what are you using? A 9 volt battery. And this here, that is the LED's forward voltage and the desired current that runs through it. And let's see. And it says, for example, assume you have a 9 volt battery to power an LED. The LED is red. It might have a forward voltage VF of 1.8 volts. So VF is 1.8. And then since you're using a 9 volt battery, that's the VS, the source voltage, which is 9. You're going to subtract that, and the IF. It says if you want to limit the current, so I stands for current forward, right? Forward current, IF. So it kind of makes sense. They have this symbol in here, and it's going this way from the battery, looping down. Here's the LED, and it's going up, like it's going back to the battery. You got to have some sort of resistance. You got all this energy and electricity from the battery, and it's zoop, and you want to resist some of that. You don't want all of it going to the LED. And then you have something right here, right? And that is your forward resistance, since you're using a red LED. And then, so when you make your schematic and you're playing with LEDs and you're making your electronic schematic, I'm pretty sure you can make the LED like blue or something, but I don't know, the computer, it looks brown to me. I'm assuming this is red. I mean, I can see the colors. I see that this is green and this is gray. The letterings are gray, but whatever. So, I might do a little quiz on this, But I turn my comments off on my videos just because I don't want people spamming my stuff, and I don't have time for all that. So I do like a giveaway or some crap. Be like, what does VF stand for? What is VS? What is this? What does LED stand for? What is this symbol for? Which would make a really good quiz. And I feel like a quiz is not really a quiz if you are like really obsessed with something. Then it's like, bring it on, right? Because you're gonna be so like enthusiastic about wanting to memorize this stuff and learn it. you know but when it comes to electronics and the fact that there's people who invented all these the math behind it, you can't just rush into it. You got to take your time. But once you apply the math of that, the formulas with the schematic, and then the final output, which is the product, then it will all make sense, and it's all good. So these formulas right here, this formula that's between the resistors, the resistor and the LED, is there something that is placed on the printed circuit board or panel, or what? So anyways, and so this bottom number is the IF, the current forward, right? I stands for current, which on this website, I don't think it talks about. This talks about the science behind it, that chemistry, science, whatever. It's basically, it gets to the basics, because you have to understand that it's all around you. There's things you can't see by the naked eye, and there's a reason why we can't see it. Can't see these little atoms. You can't see the can't say it, the electrons and the protons and the neutrons. You can't see the nucleus, you know, especially in electricity. Anyways, so where was I? And so you subtract that by that, and then you divide it by that, and you should get that. So that's what you should get, 720. So the source voltage, or VS, that's the battery. What is your power source battery? A 9-volt battery, 9. And VF is the voltage forward, which this is the typical forward voltage is the voltage which is required to make an LED light up. My bad. So this is what makes the LED light up, 1.8 volts. And you have a 9-volt battery. So you're subtracting the 9-volt battery from that, right? And then you're dividing it by the IF, which is the current forward. So how many volts does it take to, you know, to light up an LED? Well, typically 1.8 volts, I guess. But it says it varies. Sometimes it varies between 1.7 and 3.4. So you have voltage dividers. A voltage divider is a resistor current which turns a large voltage into a smaller one. Since these are formulas and I'm already going over it, I'm going to add it to this. This will just be the science part. And then since this is on resistors, these will be the formulas. So VS stands for voltage source, which, like, what is this? What is the power source? It's a 9-volt battery. And then you have, well, the formula is R equals VS minus VF, and then it's over IF. Damn. Okay, so I have to pause that so I can type all that in. So VS is your voltage source. Like, what is your power source? Like a 9-volt battery. VF stands for voltage forward, and the IF, that's the desired current that runs through it, right? And I have to put all this other stuff. You know, I don't want to try to put it in my own words. So in size out, limiting the typical forward voltage and the maximum forward current. So current stands for I, and obviously the F stands for forward. And all it just means is that it varies. It varies between 1.7 volts and 3.4 volts, depending on the color. So if I pause the video, that's because I'm typing. Who wants to make a video looking at someone type some stuff? Not me. And then I'm gonna see if I can copy this. I should have just copied the form. That was, let me see something. I'm just gonna do that. Okay. They probably got something where you can't copy the image. So it looks like I'll just leave it as is, typed out. But I can just copy this again. So I'm just going to type this out. So right here it says, let's say you have a 9-volt battery to power an LED. So since the LED is red, it might have a forward voltage, which stands for VF, at around 1.8 volts. But you want to limit the current to 10 milliamps. Okay, so you use a series resistor, okay, of about 720 ohms. Now I don't have the symbol for that. I think it's on the keyboard. I don't even think Windows 10 has that, but I'll just copy and paste that there. There we go. So the formula for that is all that, but see, I can't copy. It won't let me do it. It's weird. So I'll just do that and paste that here again. And so this will equal so you have 9 minus 1.8 over 0.010. So the VS is the voltage source, that's your battery, 9-volt battery. The VF is the voltage forward, and that is basically what this is, just like what is required to make the LED light up. Is the voltage required to make an LED light up. So yeah, real simple, right? So, oops, spelled that wrong. Okay. So I like to kind of put in my own words without, you know, typing everything word per word. Oh, I guess I didn't read this part. It says the maximum forward current is usually around 20 milliamps for basic LEDs. Continuous current through the LED should always be equal or less than that current rating. Okay, and so that's the math, and oh goodness. And so I'm going to come up here. I can't copy this. I would like to copy this picture. I think the only way I can do that is, there we go. No, don't put it there. This is the difference between, I'm not using Microsoft Word. Obviously I'm not. So I just have to open the image in okay. This is cool, resistor networks. I'll probably just add all this at the end of the video. Series resistors, parallel resistors. You have the power, measuring power. I think I can just copy some of this up to a certain point. Dang, really? It is not. Okay, I guess I'll just type it out. Okay, so basically, you have, I remember I went over this in the video about the colors of the resistor. Can I make this? No, I can't make this any wider. So you have the bands, you have a 4 band, 5 band, 6 band. On a 4 band, the first two are your significant digits. The third band is the weight, which is the multiplier. So you take these two and you're going to multiply it by the power of 10 or whatever, right? And then the last one is the tolerance. So the less bands, the less tolerant, the more bands, the more, right? So the less little bands in there, which there's this picture on what's inside of it right here, the composition of it. So this one obviously isn't going to do much. This one's going to do something, but this one's really going to resist a lot of current flowing through whatever, right? And that makes a lot of sense. But the bands inside these doesn't really line up with the stripes or the colors on it, I suppose. If we look closer, you see there's how many stripes? I feel like there's a color right here where the mouse is, but maybe I'm tripping. There is gold right here, and it's, I guess that's gold and silver, green, orange. That looks orange to me. Maybe it could be red. I don't know. I don't know. I mean, I know my colors and everything, for heaven's sake. And obviously this one can't really see it well. I see something right there, but I don't know. So, but the bands they're talking about is these stripes. And I don't know, but that's just the material inside of it. So that has really nothing to do with the outside. I'm not sure. Maybe, I mean, it has to be all connected, you know what I mean? So, and so we have 4 bands. So the first 2 bands are the most significant. Those are the most significant digits of the resistor's value. The third band is the weight value, which is just a multiplier. It just multiplies the two significant digits, which is band 1 and 2, this one, by the power of 10. And the fourth band, this very last one, that's the tolerance and how much more or less the actual resistance of the resistor can be compared to what is a nominal value. We usually use silver or gold, but I've seen both, so whatever. You have 6 band resistors. 5 band resistors have a third significant digit band between the first 2 bands. So if you have a 5 band, 1, 2, 3, 4, 5, the first 2 are significant, and the third is, right? I mean, they have a third significant, my bad. Alright, so actually, these 3 would be your significant numbers, my bad. Your fourth would be your multiplier, and your last is your tolerance. And then on the 6 band, well, 1, 2, 3, 4, for these. Well, it's kind of confusing because it's showing that this is the multiplier, and these 3 point to the band. So they usually have, which an additional band at the end indicates the temperature. The expected change in resistor value as the temperature changes. Generally, these temperature coefficient values are extremely small in the ppm range. So that's your 5 and 6 bands. There was no need to type that. I could have just combined the two. That's your 5 band, and these are your 6 bands. Okay, let's see. No need to put this other stuff. You have surface mount. Yeah, they're tiny little black rectangles. Yeah, they're usually set into place by a robot and then sent through in an oven where solder melts and holds them in place. Yeah. I haven't seen anybody do that on YouTube, but I just haven't looked it up yet. Yeah, you would have to trim the little leads there. I call them legs. Depending on what it is that you're making. Um, that's the schematic symbol. Um, oh man, this page was supposed to be for formulas, but maybe math related. Um, I mean, it would take up a lot of space though. Okay, oops. So this is the symbol. So I gotta fix my document. So this page would be on the 4-band, 5-band, 6-band. This page would be mainly on math, which that's probably gonna take up a lot of pages. And then this would be about the schematic symbols. Yeah, here in American, it looks like that, and then the international looks like that. Um, so this UF, I think that stands for microfarad, microfarad. I can't say the word microfarad. Um, I've seen this symbol, I just forgot. And so you see something like that. That is your resistors 1K. That's not a power source. The power source, well, I don't know. I still have to read this, learn more. Oh, 55 timer. Anyways, let's not waste time. Oh yeah, and I will show which websites you can go and get some of this stuff. You really want to start off with a printed circuit board. I mean a breadboard, I'm sorry. And so you can play around with it. And okay, so potentiometers. Four band, yeah. It says that no resistor is made to perfection, and different manufacturing processes will result in better or worse tolerances. So a 1K resistor with a 5% tolerance could actually be anywhere between 0.95K or 1.05K. So it says that decoding, let me just copy that. And it probably won't fit, but oh well. This doesn't have to be that big. There we go. So it just says that decoding the resistor color bands. Let me zoom in. Consult a resistor color code cable like the one below over in this side. It says that so 4.7K resistor shown here has the color bands of yellow. So if you're 4.7, that's yellow, and violet to begin. Violet. I almost said violet. Which have digit values of 4 and 7. So yellow is 4, that's their digit values. And the digit value for yellow is 4, and the digit value for violet is 7. 47. The third band of the 4.7K is red, which is the weight. Since this is a 4-band resistor, the first two numbers are the significant digits. The third band is the weight, which is the multiplier. And then the last band is obviously the tolerance. What is it going to tolerate? I mean, well, how much of it's going to tolerate. Alright, so I'm going to wrap this video up. I just wanted all the stuff I read over, the important stuff. And then, of course, the most important is being able to apply all this, okay? Because there's a lot more to it. I mean, you got the resistors, and then you have the capacitors, and they got their math. And, oh my god, right? I'm not going to paste all that. I might with this. I don't know. I mean, it's pretty interesting to me. Voltage dividers is a resistor circuit which turns a large voltage into a smaller one. Using just two resistors in series, and output voltage can be created. That's a fraction of the input voltage. So you have input voltage and you have output voltage. And you have a resistor here and a resistor here, and this is your power source. And so two resistors, R1, R2, are connected in series. They're not parallel, they're in series. And you have a voltage source. Oh, okay, so that's a voltage source. I thought it would mean like, oh, it is, okay, input voltage. But that is the voltage source is connected across them. Oh, okay, yeah. And the voltage from V out to ground can be calculated. Okay, so this, I'm gonna go ahead and add this to the document here because this is math and stuff. And all this pertains to the resistor. That's cool. So you have that, and then you have this. It won't paste. Guess I'm gonna have to type it out. So V out equals V in times R2 over R1 plus R2. That's the way I have to copy and paste these images on here. And paste that there. This will paste. Oh, it won't fit. Okay. So it's saying that the two resistors R1 and R2 are connected in series, and a voltage source Vn is connected across of them, and the voltage from V out to ground can be calculated as V out, right? Which is the which is connected to the ground. So the voltage voltage in, my bad, times R2, and then you add R1, R2, and then you divide R2 over R1, R2 combined. I'm a little distracted. And then this one, so if R1 was 1.7K and R2 was 3.3K, and you have a 5 volt input voltage, it can be turned into 3.3 volts at the V out terminal to ground. And it's just saying that voltage dividers are very handy for reading resistive sensors like photocells, flex sensors, force sensitive resistors, One half of the voltage divider is the sensor, and the part is a static resistor. The output voltage between the two components is connected to an analog to digital converter on a microcontroller MCU to read the sensor's values. So voltage out to ground, resistor 1, 5.6K, R2, and this is the power source. And I would paste that, but it would just, I think I can make some of this fit. I just got to make some of this stuff a little more smaller. This doesn't have to be so huge. If I can fit this little sentence like right there, there we go. And this is saying that here you have a R1, a resistor R1, and a photocell, which is, I guess is that, create a voltage divider to create a variable voltage output. And you got all these here, so I'm gonna stop here at pull-up resistors. And then that's that. I guess I could read the rest, right? So a pull-up resistor is used when you need a bias and a microcontroller's input pin to known state. One end of the resistor is connected to the microcontroller's pin, and the other end is connected to a high voltage, 5 volts or 3.3 volts. Without a pull-up resistor, inputs on the MCU could be left floating. There's no guarantee that a floating pin is either 5 volts or a low 0 volt. Pull-up resistors are often used when interfacing with a button or a switch input. The pull-up resistor can bias the input pin when the switch is open. So I know that this is a switch. So that's the ground, that's the button, the resistor. I've seen that VCC. But all this stuff, yo, is all on the internet. But I like it when it's, when it's put in this format, and so anyways, and so it says that the pull-up resistor, oh yeah, I think I read that. Okay, it will protect the circuit from a short when the switch is closed. So I believe this is open, and then if it's down, like connected, is closed. Or it might be the other way. Maybe this is closed, and when it's connected, it's open. You know how that stuff be opposite and shit. So in the circuit above, when the switch is open, the MCU's, the microcontroller's input pin is connected through the resistor to 5 volt. When the switch closes, the input pin is connected directly to ground. Okay. Open, and if it's connected, close. And that is that, folks. See you later.